Let's now take a look at water flow in the large intestine. So the large intestine is not going to be putting water out. The function of the large intestine is to absorb water from the lumen. If we do not absorb water, we are going to have a situation with diarrhea. What we're going to talk about after we look at the water absorption mechanism in the colon, we'll look at what happens during cholera. So water absorption in the colon, very simple, is going to be much like the process of water secretion in the small intestine. Our primary driving force here will be, of course, our sodium potassium ATPase. This primary active transporter is going to be hydrolyzing ATP and using this energy to drive sodium out. We have sodium transporters on the outside, on the apical surface of the cell. We have multiple transporters here to transport sodium, to transport bicarb, to transport chloride. And the most important thing to remember here is that the bulk chloride will come in through channels. These are separate chloride channels. This one in particular is a bicarbonate chloride antiporter. This will be coupled to the activity of a sodium proton antiporter, so that we have our sodium chloride moving from the lumen, being extracted from the lumen into the cell. The basal surface ATPase transporter will now pump the sodium into the interstitial space. There are non-regulated chloride channels on the basolateral surface that will respond to the chemical gradient that is being established by the chloride concentration increasing in the intracellular compartment and lower concentration outside. Sodium, of course, comes from our dietary sources. Now, where does the bicarb and proton come from? This, of course, will come from metabolism. Recall that CO2 is being generated by oxidation of fuels. When we combine this with water, with the enzyme carbonic anhydrase, we are now able to generate our bicarb ion and our proton, which will drive these pumps. Very simple process. We have sodium chloride coming from the lumen of the large intestine and moving into the interstitial space, and so by the basic principles of osmotic pressure, we will have water being reabsorbed into the body. Now again, this is the last opportunity for the body to absorb water in the intestinal system, the large intestine. If we have too much water resorption, then we have constipation. If we have too little, we have diarrhea. So this is a very important balance. Now normally this is balanced by the amount of fiber in our diet. So remember that fiber is osmotically active, and it holds water by binding through hydrogen bonds. This water bound to the fiber in the lumen of the intestine is going to be less available for being absorbed into the body, and so that increases our concentration of water in the lumen and prevents constipation. If we don't have sufficient fiber, water will follow this chemical gradient, and we will have compacted stools. Now, what happens under the worst case scenarios? Now, picture this system here. In reverse. So if this is our cell, we are going to be having our normal sodium potassium ATPase. But we are also going to have on the basal surface here our tripartite transporter, which is going to be transporting sodium in, potassium in, and importantly, chloride ion. Now, under normal circumstances, the flow of ions coming in to the body is going to be the predominant activity. Sodium is being pumped from the lumen into the interstitial space. The chloride is being driven in. Now, if we have an excess of chloride moving in this direction, and we have an escape path for chloride on the apical surface, what we can potentially do is to take the chloride and put it out into the lumen of the large intestine. Sodium that's being pumped out of the cell will naturally move to the lumen to neutralize the charge on the chloride ion. So now we have a bulk flow of ions moving into the lumen. Water, again, basic physics, is going to move with the ions to dilute the ions by osmotic pressures. So what controls this? This chloride channel is CFTR. The cystic fibrosis transmembrane regulator. This is a regulated chloride channel. How's it going to be regulated? By the same mechanism we saw before with vasointestinal peptide. Cyclic AMP is going to activate this channel. G protein will activate the adenylate cyclase enzyme that will convert the ATP into cyclic AMP. Now, what happens in cholera? Under normal circumstances, the G protein will be cycling between active and inactive. And this will be dependent on receptors on the cell surface. In cholera, we have what's called ADP ribosylation. And this is essentially taking the ribose structure with the adenine nucleotide and covalently modifying this G protein in the active state. If this factor modifies this so that this is constitutively active now, we will have constitutive activation of adenylate cyclase. We will have continuous production of cyclic AMP. So in cholera, our concentration of cyclic AMP rises dramatically. What this does is it stimulates the CFTR chloride transporter into a permanent active state. Permanent being until we can inhibit the cyclic AMP, reduce its concentration. So this ADP ribosylation event occurs by the cholera toxin. The cholera toxin is an enzyme that mediates the ribosylation of this G protein. So again, the G protein is ribosylated. It remains in an active state. It continually activates adenylate cyclase. Adenylate cyclase enzyme is activated at all times under these conditions, converting ATP to cyclic AMP, increasing the concentration, and therefore continually activating the chloride channel. So this chloride, instead of going through the normal path of the regular diffusible chloride channel, the single ion transporter, it's being pushed out into the lumen. The sodium follows, the water follows.